Sparse pickings. How's everybody doing?
Good.
All right, how many of you are familiar with all the cryptography stuff going on in the world? Anybody have any idea about it? Anybody know what Q Day is? Or heard of Q Day? We're going to talk about it. There's some really interesting migration patterns that we're going to have to do inside of cryptography if we want to be secure kind of going into the future. And it's not wait until 2035 to get it done. It's start now. And there are actionable items that you can do in order to do this. And it's not difficult. Now, the math is not something I'm going to dive into, nor do I expect you to dig into it unless you're a mathematician. All right, so we're going to dive into post-quantum cryptography. So a nice little quote, cryptography never dies, it just gets factored. Who am I? My name is Charlie Goldner. I am a penetration tester. I'm a student, I'm a leader, I'm a dad. Kind of why I'm wearing my dad shirt today, celebrate Halloween. I got my MSISE from standardization. I've got my GSE, all the obligatory fun stuff. I work with some other amazing hackers at CounterHack. And I work with SANS sometimes. All right, let's talk about cryptography today. So I'm sure, hopefully everybody understands what asymmetric and symmetric cryptography is. So your asymmetric cryptography, oftentimes known as like your public key encryption, public key infrastructure, PKE, PKI, right? Those kind of terms and terminology all wrap around asymmetric cryptography. Then we've got symmetric cryptography, which is your shared key. Like I have the same key that you have. You can't tell if I'm actually me, and I can't tell if you're actually you, but we both share a key. Now, we use both of these in conjunction together today in order to communicate all over the place in lots of different technology stacks. Now, your classic asymmetric cryptography systems are all based on some sort of math, typically with some large numbers, oftentimes large prime numbers, which is really the threat. In symmetric cryptography, you have a choice of AES, and you pick the bit size or your flavor, kind of like ice cream. But you get vanilla, and you get more vanilla, and then a lot more vanilla, right? So 128, 192, and 256. Pretty easy. Now, there are two, quote, theoretical algorithms that are out there, or the algorithms themselves aren't theoretical, but their application and their effect on cryptography are really the theoretical part, because there's no quantum computer to test them on yet. Now, Grover's algorithm provides an attack buff on symmetric cryptography. This one's not as big of a concern because we can pad it out, right? So your AES 256 ends up being like AES 128. Right? So it halves the bit size of what you're using for AES or symmetric cryptography. So if you're using AES 128 today, it's really AES 64. And so it's time to move on and go up to 256. Almost all of your modern systems are going to support that, and you'll be fine. That one's not as big of a concern because it's an easy switch. Now, obviously, you want to test your systems out before you make that migration. This is the one everybody's worried about, Shor's algorithm. Shor's algorithm, well, back in 1994, he discovered a very efficient quantum algorithm that could be used to solve those large prime number problems on a quantum computer. Now, it's still, again, this is still theoretical because there's no quantum computer that this algorithm can be tested on. But it posits that all of our asymmetric cryptography that we're using today is going to be broken. Everything. RSA, ECC, Diffie-Hellman. Now, this is important because what's that initial setup in an encrypted connection? The asymmetric side. And so if that's broken, I know what your shared key is, your secret key that you use in your symmetric encryption. This is the problem. Now, this also posits that it needs to have a cryptographically relevant quantum computer. Now, on the bottom right, you can try and emulate this. I pulled this down from Google. They have some Python code that goes through and allows you to build out trying to factor prime numbers. You can't do very large prime numbers because, well, our classical computers can't really do that very well. But you can do small numbers and start factoring them out pretty easy. They give you the full code. You don't even need to worry about anything until you're trying to factor large prime numbers, and then it's not going to work. Now, what is a cryptographically relevant quantum computer? A system that can actually factor those large values that we use today for asymmetric cryptography. Now, there was a paper that came out, I believe it in not too long ago, by these two gentlemen, Gidney and Eckers. They said you need 20 million physical qubits in order to break 2048 RSA. Now, those physical qubits are made up of logical qubits, and it's just a lot. We're nowhere near that today, but it could happen any day. They can make some sort of breakthrough, et cetera. Now, quantum computers really aren't doing that great just yet. If I asked you to factor the number 21 into two prime numbers, what would you get? 3 and 7. Those are two prime numbers, pretty easy. It takes a quantum computer a little bit longer than what you just did, just a little bit. But that's the best it can do as of the research that's been published. Obviously, all of that's in the public realm. And what happens on the private side, who knows? Now, what has NIST standardized? What are the different types of kind of post-quantum cryptographic algorithms in place? We have two different avenues. You have your digital signatures, and you have your key exchange, or key encapsulation mechanism, rather. Underneath your chem, you'll see that term quite a bit with the post-quantum cryptography in the algorithms. That's always specified now. And same thing for your digital signature algorithms. So you'll see DSA and chem. That's really what the two nomenclatures are all about: key encapsulation, digital signatures. And they've stuck to that with the naming convention of all these new algorithms, which is useful. It's helpful for us as we're doing some implementation. Now, underneath your key encapsulation, you have two, what you could say are the math behind it. The math behind the standardized ones for ML are module lattice. So in the name, it tells you kind of the math behind it. Module lattice key encapsulation mechanism. Your code-based, we'll get to that here in just a little bit. There's been an approval, a provisional approval at least. They still have to draft the standard for HQC. It is what's known as a code-based key encapsulation mechanism. There's another one that's been around since like 1970, 1960s. It's been around a long time, but it wasn't used for this, and we'll get into that here in just a little while. Now, on your digital signature side, you have two types. You have your stateful and your stateless. Now, there's a big difference between the two and what their use cases are for. Now, all of the kind of algorithmic back end of each of the standards, so MLChem, it's crystals Kyber, crystals dilithium is MLDSA, Sphinx, it's a stateless, so SLH, stateless hash, and then it's DSA for digital signature algorithm. Now, I don't know what they're going to name Falcon. Falcon has also been approved, but it still doesn't have a standard, or it does have a standard, but they haven't come up with like a name, so they just call it Falcon. But that might change. Things in this space change pretty often. Now, what is module lattice based? Everybody's seen that little dot game where you connect like one line and everybody has a turn to like connect a line and then you fill in a box? That's kind of like what a lattice looks like, except instead of 2 dimensions, you have like thousands, millions of dimensions. Now, in our minds, that's kind of implausible. But like for a computer, it's not, because it's all just algebraic equations. It's just multivariate, huge list of variables. And so it's all based on vector math. How can I get to a specific vector to identify the secret key? And they've added in some error. That way it's a little bit even more difficult for a computer to guess what that end vector or that answer to that problem is. That's that core task, that hidden noise. It's very, very difficult. Now, your module lattice space, again, your ML-Chem and Falcon, ML-DSA. So both of the crystals algorithms are module lattice based. And the reason they started going with different types of math and different types of algorithms, like module lattice based and code based, is because, well, these things we're unsure. We're not sure if these things are going to survive out in the wild. Your stateful hash based. NIST actually standardized 2 of these. They're called XMSS and LMS. Now, both of these are based on what are known as Merkle trees. Anybody know what a Merkle tree is? Anybody ever heard of Bitcoin? So Bitcoin uses something like this. It's a Merkle tree structure. And so it's all based on how a hash gets created, and it's just a tree full of hashes. And how can you prove that a hash was done, or the work was done? How can you prove an authentication path? And so these both use that same type of mechanism, and XMSS just adds some XOR into it. Now, the difficulty with both of these are they have to keep track of the state. Now, what that state means is in that tree, you have a path. And in that path, that's one key, or a leaf. That's a one-time key. You can't use that path again. You can't use that key again. So that path equates to a key. Now, if you can't use that key again, well, I have to keep track of all the keys that I've used. And so that's why it's known as stateful, because you can't reuse a key. Now, it's not meant to be a everyday use type of solution. This is meant for things that are long-lived, not anything that you need to reuse every day. And it's not useful in like a TLS connection. That's why these aren't primary in what all the post-quantum items are going to be in the future, all the post-quantum algorithms for general use. That's why Sphinx was approved as a stateless. Your stateless I take that back. Stateless, not stateless as the primary use. It was dilithium as the primary use. A lot of terms. Now, this is another digital signature algorithm here under your stateless for Sphinx. Sphinx uses the same mechanism. It still uses Merkle trees, but it doesn't have to keep track of the state of what's happening within that Merkle tree structure. And so it can just generate a key, and now that key can be used, and it can move on. And so all that state means is like if a system's resident and it's living and it's online, if that system gets torn down and then built back up again, you've lost track of the state of the keys that you've used. And so if you try to use the same structure, it's going to break. Or somebody could break that cryptography that you're leveraging. With Sphinx, you don't have to worry about that system getting rebuilt because you're not keeping track of the key every time. A couple of your code-based, HQC, this is the one that has, it's a draft standard right now. They're going to probably publish the actual FIPS standard within the next year or two. It does take a lot of time for that to happen. HQC is going to be the backup to ML-Chem. Right, so ML-Chem is going to be the primary as the post-quantum cryptography for key encapsulation. Now, the one that's been around since like the 1970s is Classic McLeese. Classic McLeese, the biggest reason they they didn't really choose that, I'm not on the board, I don't know what the reasoning behind NIST, but you can theorize. Classic McLeese uses huge keys. They're extremely big. You think an RSA 4096 key is large. The Classic McLeese, like at a level 5 of security, would be like a megabyte in size or larger. They're very, very large keys. And that's why it's not very efficient, but it's very secure. This is all built on error correcting codes, so you've got to sort of try and find the message based on what was delivered with that error on top of it. So essentially it looks like this. Sent you a note hidden in an enormous crossword puzzle. Messed up a few letters, but if you know how to decode that, then you can get the message. Now I had ChatGPT generate this image. I actually had AI generate almost all the images in here. And so some of the letters don't look right. So it's still a little jumbled. Now there are different security levels for each of the algorithms. So they each have a specific little variant. Your security level 1 is essentially where most people are at today with their classical algorithms. You're using AES 128, and so the post-quantum equivalent is going to be your ML-Chem 512. There is some conjecture that it's not very secure, even with ML-Chem at 512. I have seen some research within the last couple months that it's not super secure. HQC 128 and then Falcon 512. Now, if you want to get that level 5 security, you're thinking of like, I know we're kind of in a government space or near government facilities, and you're thinking about things like information that has to last and be secure for a very long time. You're probably going to be looking at a level 5 of security. Your key sizes do increase. Your ciphertext and your plain text do increase in size, and that's one of the big concerns with moving to post-quantum cryptography. Now, there are other candidates that are out there. Classic McLeese was one of them. Depending on where you're at in the world, NIST standardized some, and a lot of people use the standards that NIST specifies. But not everybody agrees on that. So like in Europe, they still think like some of the other candidate algorithms could be used instead, or they're going to include them to make sure that they're available for use. And really, it's just not spreading yourself so thin on the algorithms that are standardized. So we have other algorithms to use in the event that something happens. Digital signatures, there are a ton. The key encapsulation side, there are maybe, I don't know the exact number. There was like 10 or 12 candidates. There wasn't very many. But digital signatures, there's probably like 30 or 40. Mayo is one of them. The math problem behind it, it's kind of funny. It's a pun on the name. It's the oil and vinegar problem. It's kind of ironic. Now, what about the rest of the world? There are standards that are out there throughout the rest of the world on what is chosen or what could be implemented. ISO has a couple of standards for, and this is where I was mentioning, the Frodo-Chem and Classic McLeese. On the international stage, like in Europe, they appreciate the fact that these have been around for a really long time, and they've been proven, at least Classic McLeese. And so they think that one is still a solid choice. In the EU, the ETSI, they published some information about migration in conjunction. So it was like the Dutch, the Germans, and the French. They all came together and collaborated on this. And the Dutch actually published what's known as the PQC Migration Handbook. I'll show you what that looks like here in just a little bit. Now, is it really being used in the world? Well, it is. Apple started using it over almost 2 years ago now. Signal migrated over 2 years ago. Now, they're not using strict post-quantum cryptography. They're using like a hybrid approach. And we'll talk about what a hybrid approach is here in just a little bit. Google's been doing this for quite a long time. They've been part of the standardization process and testing a lot of these items. They use it internally within their own infrastructure. Microsoft's been doing a lot of research in this space, but they finally released some tooling for Windows in this year. AWS has their own cryptographic library that you can leverage, and you can actually start creating keys within AWS KMS that are ML-Chem. OpenSSH, they took a while to get on board. OpenSSH, I think right now is on version 10 something. But 9.9, which was released earlier this year, probably around summer, they finally started supporting ML-Chem as a key exchange or key encapsulation mechanism. The PQC capabilities matrix, if you Google that term, you'll come across a website that has the capabilities of all the different types of libraries and solutions that are out there and what they support and what they don't support. It's a really useful tool to have on hand. What about those mitigation options? So what can you do today to get ahead of the curve? Well, you're trying to mitigate what's known as the harvest now, decrypt later, store now, decrypt later. There's a couple different terms that go with that. It really depends on what your risk level is. If you are in that government space or you're providing cryptographic material to others, you're probably going to need to think about switching now. And we'll go through kind of a timeline for depending on what you do as far as work or where you work. Q-Day. Q-Day is supposedly that, it's a kind of a coined term, like a lot of things in our industry. But Q-Day is the day that a cryptographically relevant quantum computer comes online and can break our current classical asymmetric cryptography. And so you want to avoid having to make that emergency change at the end because you're going to be well behind the power curve. You've got 3 mitigation paths to choose. You can go QKD, which is quantum key distribution. You can go full PQC, never go full PQC. Or you can use a hybrid approach, classical and PQC together. Option A. Now, quantum key distribution, you've got quantum key distribution devices in different locations. There's a physical limitation between these items. You have about 100 kilometer distance. They got to be connected via fiber, lots of additional hardware. The biggest issue with this is there's not a lot of good standards or a standardized way of tackling this problem in the KQD space. There are solutions out there, yes, but there's no standardized, here's how you keep this solution secure, here's how you should set it up. Even the security of it is still suspect. So really you've got 2 mitigation paths. Go full PQC. Now you're depending on unproven cryptographic schemes or cryptographic algorithms. Now that's not necessarily true. Unproven, they've gone through the standardization process. People a lot smarter than me, mathematicians, cryptographers, cryptographic analysts, cryptanalysts, they've gone through and done a lot of the legwork to try and verify that these things are solid. However, they haven't been in the real world in use in mass. And so that's part of the problem. Now, if you want to go full PQC, and this goes for hybrid as well, you have to be able to have what's known as cryptographic agility, which is being able to switch really fast. Because if some new novel vulnerability comes out, well, I can't be like, well, I'll just wait till somebody else figures it out. It doesn't work like that. Now, you typically don't need any additional hardware with post-quantum cryptography. It's really a software change. As long as your software stack can support it, you shouldn't have a problem. Hybrid PQC, this is the one that most people recommend because you're using what you already know, what you're already using in combination with the new stuff, the new kid on the block. Maybe I should put new kids on the block on there. So it's the classical and post-quantum cryptography together. When you do that asymmetric key exchange, instead of normally when you have kind of one validation done on the exchange, there's 2. There's one for the classical side and one for the post-quantum cryptography side. And if both of them don't agree or both of them don't pass that test, then that assumption is thrown out. Now, both the full post-quantum and hybrid can increase the complexity or can increase the attack surface due to the complexity of the implementation because there are a lot of different things to take into consideration. Again, this one also doesn't require additional hardware typically. It depends on your types of systems that you're using. Now, what is cryptographic agility? Now, there are some kind of definitions that are out there. The post-quantum cryptography migration handbook from the Dutch has a really nice, it's pages long, but really the way I look at it is decoupling your cryptography from the infrastructure. Instead of having cryptography, or anybody work with networking gear before? How you can have the crypto mod inside your Cisco device or your network device? That's no longer a thing. I don't need that anymore. There's actually a protocol called SKIP. And SKIP allows you to request a key from a key provider and then use that key in your communication. And so you don't have to have the cryptographic module on your device anymore. So it's like an API. Right? And so it's decoupling that cryptography from whatever the system that needs it. That allows you to make some changes very quickly. Right? It's instead of using monolithic architecture, we've decoupled it. There are some commercial solutions out there. I just did a research on one from a company called Quantum Exchange. There's another company out there that does this called QSecure, KU and then secure. Both of them offer this type of capability. Right? So you plug in a container, you host a container in the cloud if you want to do it that way. Your network devices can also host containers, and that becomes the key provider for that device. So having some agility and being able to migrate quickly in the event of an issue on the classical side or the post-quantum side. All right, so do you need to switch? Well, that post-quantum cryptography migration handbook, the PQC migration handbook from the Dutch, I use some of the information from that to come up with these items, and it's actually really well done. So they have the first, or the kind of 3 tiers. You have your urgent adopters. So if you're worried about long-lived secrets, needing to keep it secure for a long time, you should already be looking at switching if you haven't switched already. Your regular adopters, these are, most businesses will fall into this category. They don't handle any types of sensitive data. Sensitive data is, I guess, relative, depending on where you work and what you do. But infrastructure type data, critical infrastructure, government secrets, national secrets, maybe financial data, depending on who you're doing financial transactions for. Cryptography experts. Now, you think of like the people who provide the capability for you to host your infrastructure on, and you consume things like cryptographic algorithms from them. Your cloud service providers, the government agencies that provide cryptographic primitives to military units, things like that. How do you switch? Well, you first need to understand what you have, what you're using. It's doing an inventory, all your supply chain dependencies in the software you use throughout the entire life cycle of that device or whatever it is. It's just like when you have your computers, right? You need to do some sort of asset management or configuration management on the systems that you own. It's the same for cryptography. So it's establishing some sort of asset management or configuration management for your cryptographic primitives that you're using. Establish a policy if you don't have one already, and then review it as you go along. Understand what your risk level is, so conducting your own risk assessment. There are going to be some costs of migrating. Some of them are operational, right? So sometimes you might have some downtime in order to implement something. Not everybody's going to be able to support it, so you have to have some fallback mechanisms. Are you bound by any regulatory requirements? Do you have to switch by a certain time? Are you supposed to use a certain type of algorithm? The NSA has their, I think it's the CNSSI 2.0, where they establish like what algorithms you can use. And then collaborating with others. Right. Anybody want to see this in real life? Yeah. All right, so there's a couple things I want to show you. The first one, actually, before we do that one, let's look at the post-quantum migration handbook. So this is the PQC handbook from the Dutch. It's very well done. It goes through, literally almost everything I talked about in depth, quite a bit. Asset management, migration planning, execution, developments throughout the world, and then looking at the different primitives that exist. Oops. They even have little process life cycles. So again, you can find this online. You just look for the PQC Migration Handbook. It's a good book. Now there's a project called Open Quantum Safe. Now Open Quantum Safe has done a really good job of making this accessible to the world. And a lot of your commercial solutions that are on the market now leverage the cryptographic library that these folks have built. It's called liboqs. So liboqs, it's all open source. It's all, you can review the code. They've got C code implementations, right? So if you need like the actual source code of how to implement this in a software stack, you can do that. They have their GitHub repos, quite a few actually. The library itself, so liboqs, you can use it as a provider to OpenSSL. And then they've got some demos. The demos are really nice because you can stand this up kind of locally without having to worry about anything. You don't have to go over the network anywhere. This is liboqs. Talks about all the different fun things. The OQS provider. The demos, they've got different technologies available here for you to stand up and leverage post-quantum cryptography using that software stack. So if you're running Nginx, you want to run it in OpenVPN, whatever it is, they've got some demos for it. Now, you got to take what they give you with a grain of salt, and you're going to have to do some troubleshooting. I've spent many hours trying to figure out why something was broken, and it was really because the naming convention has changed from using a dash to not using a dash, or vice versa. It's ridiculous. But again, these things change quite a bit. Or you can use their pre-built containers, and you don't have to worry about it. So their pre-built containers, they have curl, they have all of those items that are listed on that demo site, and then some. So pre-built containers that allow you to stand up a specific capability and then go actually do it. They have a test site where you can test your implementation or even use their stack. So it's a TLS 1.3 site, and they walk you through like, here's how you can test it. You can do some packet captures. Now that's one of the biggest problems that you face with dealing with this technology is not all of the software that you have and that you're normally used to using can understand it yet. So one of the demos that they have is a custom compiled version of Wireshark, which we'll see inside of the demo here in just a sec. So I have two versions of Wireshark running. One, I can just pull up a PCAP in case things go awry. The other one, I'm just going to capture traffic live. So we're going to, this is running in a container, and I can't zoom in. That sucks. We'll see that in here in just a sec. Right, so curl, if you want to go look at like their website and curl a specific algorithm, like they have a different algorithm hosted on each port. Each one has a specific signature, each one has a specific key exchange mechanism, and so you just curl that port using their container, which they give you on this same site, and you can see it implemented. So I can go, hey curl, let's make sure Wireshark's listening. I also am storing the SSL keylog file so we can actually look inside the encrypted connection. This one's going for MLChem 1024. And there's the communication. No big deal. Now inside of Wireshark, if I go look at actually before, let me go add in or inject my secrets. Oh, I had to restart curl, so I have to do that keylog file again. it's not working. Well, we have a backup plan. So in this communication here, what you're going to see in Wireshark or things of that nature, I wish that this could be much bigger. Let's see. Oh, this one will zoom in. Why wouldn't the other one? In your non-custom compiled versions of Wireshark, all you're going to see is an OID instead of the actual algorithm that's being used. That's part of what you do when you're building the custom compiled version is you define what that OID refers to. So if you're seeing things like that, there are lists out there. The IETF actually has a list of the OIDs, so you can identify what the algorithm in use is. So in this one, the certificate being used is the MLDSA certificate. So that web server certificate on the web server is signed using the MLDSA. So that's a security level 5 certificate. Now in my client hello and my server hello, notice how some of them show up as unknown. It doesn't know how to understand those because the OID is not identified. On the SSH side, you can use this in SSH as well. Your SSH config, so if we look at our SSH config, just really quick, OQS, SSH, SSHD. So this SSH config only leverages post-quantum cryptography for key exchange. It's the only key exchange that's allowed. No classical is allowed, so it's using either hybrid or pure. No classical at all. For the host key algorithms, it does the same, although at the end I put in RSA and ED 25519. So if you still want to leverage things like the classical specifically, you can. This is also their but open quantum safes, open SSH build. So you have all of your hybrid, pure, and then classical algorithms there. And then you can create your keys and build them out and leverage keys for post-quantum cryptography. There is a tool that I built, really this is just Python that iterates through the SSH keygen command and builds out all the keys. If we look at the size of each of the keys, so based on the algorithm, here's what the bit size of each of those keys ends up being. And then the NIST security level that equates to it. So if you want to use like a security level 5 SSH key to establish a connection, depending on the key size, if you want to keep it smaller, your best bet for a security level 5 is to use ECDSA with NIST's P521 elliptic curve, and then Sphinx, SHA-256, F simple. And these names get really convoluted, and they get very long. Now that I have a set of keys, I can just use them. So I have inside my SSH directory, I've got a security level 5 key here. I've got another one here. One is hybrid. The other one is not. And then I've got, actually no, these two are hybrid. This one here is strictly post-quantum. So I can say SSH, pick a key. Let's say ID Mayo 2. And it works. It doesn't take that long to make that key exchange. Now, granted, it's only going to local host, but both sides would have to agree. And now I've got a post-quantum protected SSH connection between two systems. So it's not super difficult to get this done. All right. Anything anybody else wants to see? Questions? Yes?
So when do you think Q-Day is going to arrive?
When do I think Q-Day is going to arrive? You know, like if you follow what's going on, you know, things happen so rapidly, especially with AI. Honestly, I don't even think 2035 is going to be a target. Yes, they're pouring a lot of money into this, but I think the capability will come out to us a lot later than it actually shows up. Because things are going to happen behind closed doors before they go out into the public because of national security reasons. Yeah. If you're interested in like actually doing things on a quantum computer, so speaking of IBM, IBM has a program that you can get into. It's called KISKit, KISKIT, and you can actually code quantum circuits and have them run on a quantum computer, and it's free. It's actually a really cool community. You build out your code in Python, and then you host it up there, and you get some time. It's like a shared space where you can run your code on a quantum computer. All the major cloud providers have a quantum computer or quantum capability inside of them. So it's not cheap, but you can run some quantum workloads in there as well. Yes?
Are you going to post your slides for this presentation?
I can, yeah, absolutely. I can post the slides.
And BSides should be posting the presentations within the next couple of days.
Okay.
Tomorrow. Should be tomorrow.
Oh, wow. Awesome.
Cool. Yeah, so BSides will post them tomorrow. Yes?
Does this change, do anything to affect things like TLS fingerprinting?
That's a great question. So does it affect TLS fingerprinting? And it does, because the keys that you're using change. Right? And so the fingerprinting is all based on that key. So if you're using like JAW3 hashes to identify specific targets, then that hash is going to change not significantly, but it'll change. It's just like if your key changes, your fingerprint changes. Yeah, so your hashes will definitely change. Yes?
So when you ran your demo, it was using negotiating in TLS 1.2, right? So with TLS 1.3, we know that part of its advancement is the fact that it does kind of a pre-selection of algorithms already defined, right? So instead of having a giant suite of ciphers that are here, pick from this, and then we'll negotiate, it kind of says, here's the ones that we're allowed to use, and I've already preceded the knowledge of what my portion of the encryption handshake is going to be. So based off what you were saying, what is that going to look like from if it was a TLS 1.3 connection, where you're not going to have a list of ciphers that's going to be pretty predictable? And did they do the exact same thing where they have kind of like, I guess, led with or selected known PQC algorithms that they want to use, or is that not even on the cards yet?
So you can establish, like on your server, what PQC algorithms you want to use, like on your HTTP server. So like in the Nginx configurations that they have posted, you can say, I only will support these algorithms. So you can specify that just like I did in my SSH config, so where that I will only accept these algorithms and nothing else.
But like I guess since it's still developmental, there's not like vendor support. Like if you were to pull a common library, like libSSL or something like that,
Yeah.
and you can overwrite it for sure, but did they already make those selections yet, or is there any kind of like, I guess really to put it another way is industry and folks that deal with this on the regular, have they already kind of picked their favorites of where they think things are going to go for either speed or security or what have you?
The algorithms themselves?
Yeah.
So it's the primary standards. The primary standards are going to be kind of the way to go. It's using ML-Chem, ML-DSA. Those are the ones that are like the general use, and everything other, all the other items or all the other kind of ones that are being standardized or even candidates, they're just backups. Yeah. For general use, it's ML-Chem and ML-DSA. Yeah.
So for most organizations, if you're thinking about this from sort of a threat modeling perspective,
Yep.
would you say that we're really looking at nation states that are going to be building this against each other? I mean, your average person is not going to have computers to bring to bear
Right.
on the problem. So obviously there can be people within a country that might be interested to their own government, but by and large, I would say, would you agree that most orgs are not sending things out today? I mean, I guess I should back and say, do you really believe that the capture now, decrypt later situation or possibility is realistic for most? I mean, I appreciate where we're sitting, but in general, I mean, that seems like for most organizations that's such a remote possibility just due to the engineering problem of capturing and storing all that data. So you really think this is anything other than just nation states kind of building against each other initially?
I think you're absolutely spot on. I think it is more of a nation state thing right now, but I think also it has to depend on, or it does depend on, who you support within your organization. Right? Like if I'm AWS, or if I have my stuff hosted in AWS and I'm in GovCloud and I provide services to the DoD, I probably should consider looking at this sooner rather than later. If I'm, a little software company that doesn't do much besides support a couple of different states within our location or our area, I wouldn't consider it like a super big priority. But if you are supporting like government contracts, things of that nature, and you're hosting your stuff in clouds, and one of the things I looked at when I was testing that solution from Quantum Exchange was they plug into the WAN side. Right? That was where the kind of big migration pattern starts, as you do it from your WAN connection, so site to site. Everything internal might still be just fine, might still be using classical cryptography, which is fine. But on your WAN connections in between site to site, where it can be captured, that's really where you've got to be considerate of what encryption you're using. Other questions? All right. Here's my contact information. My GitHub's kind of sparse. Most of my stuff is done on the private repo side. But if you have any questions, you can reach out to me via email or on LinkedIn. LinkedIn's probably a little bit easier. Thank you very much.